In this video, we delve into the reactive world of heteroatomic compounds, molecules where oxygen, nitrogen, or sulfur stand at the center of chemical transformation. We begin with ethers and epoxides. While simple ethers remain remarkably stable, their cyclic counterparts, epoxides, carry immense ring strain, making them highly susceptible to nucleophilic attack. Then, we'll explore amines. You'll see how a poor leaving group can be converted into an excellent one through exhaustive methylation, leading us to the regioselective Hofmann elimination. Finally, we'll examine organosulfur compounds, focusing on the nucleophilic reactions of thiols and sulfides. Let's visualize the intricate mechanisms of nucleophilic substitution. Our journey into heteroatomic chemistry starts now. Section 1. Ethers. Cleavage by hydrogen halides. Ethers are generally unreactive, so their cleavage requires strong acids like HI or HBr. These reagents are particularly effective because iodide and bromide ions are powerful nucleophiles in protic environments, whereas chloride is generally less reactive toward ether cleavage. Depending on the structure of the alkyl groups, the reaction will follow either an SN1 pathway, driven by carbocation stability, or an SN2 pathway, determined by nucleophilic accessibility. When one of the alkyl groups can form a relatively stable carbocation, such as a tertiary cation, the reaction follows an SN1 pathway. First, the ether oxygen is protonated to create a good leaving group. Then, the CO bond breaks heterolytically, generating the stable carbocation. Finally, the iodide ion attacks this intermediate, resulting in an alcohol and an alkyl iodide. If the alkyl groups would form relatively unstable carbocations, such as methyl, primary, vinyl, or aryl cations, the reaction must proceed via SN2. Just like the SN1 pathway, the process begins with the protonation of the ether oxygen to create a good leaving group. Then, the iodide nucleophile performs a backside attack on the less sterically hindered carbon. The leaving group is displaced in a single, concerted step, yielding an alcohol and an alkyl iodide. Section 2. Epoxides. Regioselective ring opening. Moving on to epoxides. Unlike open-chain ethers, these three-membered rings possess extraordinary ring strain, which makes them highly reactive toward a wide variety of nucleophiles. Under acidic conditions, the epoxide oxygen is protonated first, which significantly weakens the CO bonds. This process induces a carbocation-like character at the more substituted carbon, as seen by the larger partial positive charge in the transition state. Because this substituted position can better stabilize the positive charge, the nucleophile selectively attacks this site despite the steric hindrance. The nucleophile still attacks from the backside, leading to inversion of configuration at the reactive center. We can see this principle in action when a weak nucleophile, such as an alcohol, also serves as the solvent. The solvent molecule then acts as the nucleophile, selectively attacking the more substituted carbon. This leads to the formation of a regioselective product with inversion at the reactive center, clearly illustrating how these mechanistic principles apply to real-world solvolysis reactions. In neutral or basic media, the regioselectivity of the epoxide ring opening is governed by a straightforward SN2 mechanism. Unlike acidic conditions, there is no prior protonation to weaken the CO bonds. Therefore, the reaction is driven purely by the accessibility of the carbon atoms, making steric hindrance the dominant factor. The nucleophile targets the less hindered carbon to minimize steric repulsion during the transition state. As it performs a backside attack, The CO bond breaks and the ring opens, forming an alkoxide intermediate. It is important to note that if the attack occurs at a non-chiral center, the stereochemistry of the existing chiral center remains preserved. In the final step, the resulting intermediate is protonated by the solvent to yield the stable neutral product. This sequence clearly illustrates how steric accessibility dictates the regiochemical outcome in basic ring-opening reactions, leading to the formation of a product where the nucleophile is attached to the less substituted position. The synthesis of 1,2-diols varies significantly depending on the desired stereochemistry. Nucleophilic ring opening of an epoxide, such as with a hydroxide ion, leads to a trans 1,2-diol. This process involves an SN2 backside attack on the ring, resulting in an anti-addition that yields the trans configuration. In contrast, 𝑠𝑦𝑛-addition is required to synthesize cis-diols. This is typically achieved using reagents like OSO4, which forms a cyclic osmate ester intermediate. This intermediate ensures that both oxygen atoms are added to the same face of the alkene, resulting in a cis 1,2-diol after subsequent workup. For a detailed breakdown of these distinct mechanisms, please check the video link in the comments. In our bodies, aromatic compounds like benzene are metabolized by enzymes known as cytochrome P450. Using molecular oxygen as an oxidant, cytochrome P450 converts benzene into a highly reactive intermediate called an arene oxide. Arene oxides are cyclic ethers of aromatic rings that react through two distinct pathways. First, they can be attacked by nucleophiles through an SN2 process. The nucleophile attacks from the backside, opening the ring with anti-stereochemistry to form a trans-addition product. Second, arene oxides can undergo rearrangement to form phenols. This pathway proceeds through acid-catalyzed ring opening to generate a resonance-stabilized carbocation intermediate. This is followed by a 1,2 hydride shift, commonly known as the NIH shift. Subsequent loss of a proton restores aromaticity, completing the transformation into a phenol. Section 3. Amines, the Hofmann elimination. Amines are poor leaving groups because the resulting amide ion is an extremely strong and unstable base. In organic chemistry, a good leaving group must be a weak, stable base that can easily accommodate a negative charge. Since the amide ion is too reactive to exist as a leaving group under normal conditions, it must first be converted into a quaternary ammonium ion, which can expel a neutral tertiary, amine, as the leaving group. When a primary amine reacts with excess methyl iodide, the nucleophilicity of the nitrogen generally increases as each methyl group is added. This is because the inductive effect of the additional Alkyl groups increases the electron density on the nitrogen, making it a progressively stronger nucleophile until a quaternary ammonium salt is formed. Treatment with silver oxide and water converts this salt into a quaternary ammonium hydroxide. Upon heating, this intermediate undergoes an E2 elimination known as the Hofmann elimination. Unlike most E2 reactions, this process yields the less substituted alkene as the major product, which we call the Hofmann product. Just as all E2 reactions require an anti-periplanar geometry, this process is uniquely governed by how easily that conformation can be reached in the face of severe steric strain. In the conformer currently shown, the other beta hydrogen is not in the required anti-periplanar orientation to undergo an E2 elimination. This necessitates a specific sigma bond rotation to achieve the reactive anti-periplanar conformation. However, in more substituted sites, this rotation forces the bulky trialkylamine leaving group into a sterically crowded gauche relationship with other alkyl substituents. This steric strain makes the abstraction of the more hindered beta hydrogen kinetically unfavorable, causing the more substituted Zaitsev product to form only as a minor component. Consequently, the base preferentially abstracts the most accessible, least hindered beta hydrogen, favoring the less substituted alkene, the Hofmann product. Additional reactions of amines will be covered in detail in a future video dedicated specifically to amine chemistry. Section 4. Organosulfur compounds, thiols, and sulfides. Sulfur is a significantly better nucleophile than oxygen. This is due to its larger atomic size and greater polarizability, which allows its electron cloud to deform more easily to initiate a backside attack. Thiols are the sulfur analogs of alcohols. Similar to the formation of alkoxides from alcohols, thiols can be easily converted into thiolate ions by treatment with a base. Because sulfur is less electronegative and larger than oxygen, thiols are more acidic, allowing this conversion to occur more readily. In an SN2 reaction, the resulting thiolate ion, acting as a powerful nucleophile due to its high polarizability, attacks an alkyl halide. For example, methanethiolate reacting with bromomethane in methanol yields dimethyl sulfide and a bromide ion in a single concerted step. Sulfides can also act as nucleophiles to attack alkyl halides, forming sulfonium salts. These salts are highly reactive. When a hydroxide ion attacks an alkyl sulfonium ion, an SN2 process can occur, displacing a sulfide leaving group to produce an alcohol. Let's briefly look back at the key reactions we've covered in this episode. First, ethers undergo substitution with strong acids like HX and heat to produce an alcohol and an alkyl halide. Second, epoxides are highly reactive due to ring strain. They undergo ring opening reactions either with HX under acidic conditions or with nucleophiles under neutral or basic conditions to yield 1-2 substituted compounds. Third, amines can be converted into alkenes through Hofmann elimination. Treatment with methyl iodide, silver oxide, and heat forms the least substituted alkene via an E2 mechanism. Finally, sulfur-containing compounds are excellent nucleophiles. Both thiolates and sulfides react with alkyl halides through an SN2 process to form sulfides and sulfonium salts, respectively. A biological equivalent is 𝑠-Adenosylmethionine, SAM, which serves as a methyl donor through a similar SN2 mechanism. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.